So, welcome everyone to our second day of Research in Options Rio 2020. And the first speaker for today is going to be Professor Peter Tankov from École Polytechnique and from Paris 7, right, Peter?
No, it's NSIO.
NSIO.
I'm no longer at Paris
Okay.
7. NSIO is the School of
Okay.
Statistics and Economics.
Yes, all right, thank you. Yes, so it's a pleasure to introduce you, Peter. Peter has done extensive work in jump diffusion models and in mathematical finance. For the last few years, he has been devoting himself to energy markets and electricity markets, and today he's going to tell us about his research. So thank you so much, Peter, for taking the time and presenting to us.
Thank you very much, George, for the introduction and also for inviting me to this conference. If anything goes wrong with the slides, please tell me, because I only see my slides. I don't see anyone. And also, it's a great pleasure. I don't know if Marco is listening to us, but it's a great pleasure to speak at this conference dedicated to his birthday, because Marco actually played an important role in my scientific career. One of I think the very first conference, academic conference that I attended in Lyon in 2001, to which Rama invited me, there was a session in mathematical finance. It was, I think, a French probability conference with a session in mathematical finance. There was Marco, there was also Nicole Caroui and Rama, of course. And this was a very inspiring conference, and in particular, Marco's talk on, I think it was on weighted Monte Carlo or another model calibration paper. And this really helped me to find a topic for my future PhD. So thank you, Marco, and happy birthday. Now for today's talk. My talk is about pricing in intraday electricity markets. So let me start with a brief introduction into electricity markets. So how to sell electricity in Europe. Actually, there are many different ways to do this. There are OTC contracts, spot contracts, organized markets, system services, and so on. We are only interested in the two organized markets, the spot market, also known as day ahead, and the intraday markets. Now, the spot market is a one-off market where participants submit bids on the day before the actual delivery occurs, before noon, and then at 12:55 the price is fixed and the market clears. So there is an order book in the spot market. The order book is formed from the bids of the participants. So here, this is a peak hour, 19 from 7 p.m. to 8 p.m. So you see that the price is relatively high compared to this hour, which is an off-peak hour during the night, and the price is very low. You can even have, in Germany especially, negative prices in the spot market. Okay, but then the spot market closes, and people still need to trade electricity. And it is then that the intraday market opens. The intraday market is a continuous trading market. It opens at 3 p.m. and allows continuous trading for each hour or quarter hour in Germany of the next day. And this happens up to, depending on the country, also 5 to 30 minutes before delivery. So you can trade energy, electricity, almost up until the delivery time. And in the intraday market, every delivery hour or every quarter hour of every day corresponds to a different product. So today's products are not the same as tomorrow because the delivery date is not the same. And so the lifetime of a single product in this market is very short, from 9 hours to 32 hours. 32 hours, it is the last delivery hour of the day, and 9 hours corresponds to the first delivery hour of the day. And the development of intraday markets, especially in Europe, is very much driven by the increasing penetration of renewable energy, because these markets are mostly used by renewable producers, aggregators, or other agents dealing with renewable energy. And why it is important? Why do they use them? To adjust the forecasting errors. Because if you have a nuclear power plant, then you know well in advance how much you will produce on a given hour tomorrow. So you don't really need to adjust your volume, to adjust the quantity that you sold in the spot market in the intraday. However, if you own a renewable power plant, intermittent renewable, especially, for example, wind power plant, then you may not, the forecast that you have on the day before production may not be exact. And so you will have to, as when you receive an improved forecast from your forecasting company, you may need to adjust the production that you saw on the spot market. For example, if the forecast is less than what you promised to deliver, then you will need to buy extra energy in the intraday. And in these graphs from Apex Spot, you see that the development of intraday market in Germany, so this is the volume in the intraday electricity market in the Germany bidding zone, follows very closely the development of renewable energy in this country, because really it is very much driven by renewable energy production. There are several interesting features of intraday markets. First of all, the trading starts at 3 p.m. of the previous day, but nobody actually starts trading at 3 p.m. because the spot market just closed. There is not much new information available, so people do not start trading immediately. Actually, the liquidity in the intraday markets appears only a few hours before delivery. So this is what we see from these graphs. The left graph shows the distribution of orders, order inception times, and the right graph shows the distribution of transactions as function of time to deliver. And we see that liquidity really starts to come. It's at highest just 1 hour before delivery, and it starts to come to the order book maybe 6 hours before delivery. Also, if we look at other characteristics of the markets, two important stylized features of these markets are the Samuelson effect. In other words, the volatility which grows as we approach the time to delivery. Right? So here we have time to closure, time to delivery, and this is an estimate of market volatility for different delivery hours. So we see that as delivery draws near, the volatility goes up. And also volatility may be different for different delivery hours. The peak hours are more volatile, the prices for peak hours are more volatile than for off-peak hours. Okay, the lowest volatility is for delivery at 2 a.m. in the night. Another important stylized feature is the correlation between price and renewable production forecast. So here we have plotted the correlation for Germany delivery zone between the intraday market price and the forecast of global renewable production, wind power production in Germany. And you see that the correlation here, it may not be as high, it's only about 8%, but it is really significant because 0 is outside the confidence interval. So these are two important stylized features. And actually these negative correlations, they affect negatively the profits of renewable producers, because when the energy forecast goes down, when the production forecast goes up, this means that you are expecting to produce more, the price goes down. So when you produce more, you sell it at a lower price. So what is the goal of this paper? Now, in this paper, we would like to build a theoretical equilibrium model which explains in particular these stylized features that we have seen. So we build an agent-based model of intraday electricity markets to understand the role of renewable producers in price formation and reproduce some of the observed features of the price. In the model, we have agents and agents in this case. We also have a mean field gain version of the model, but here we just have n agents, which are expected gain maximizers. They determine the strategies based on market price and the forecast of production, subject to a terminal constraint. Terminal constraint means that you will need to deliver exactly the amount that you have sold in the market. And the market price in this paper will have a fundamental component and the price input component, which depends on the strategies of the agents, and this introduces a game into the problem, games-like characteristics into the problem. Now, there are a few studies in the literature. One can distinguish three categories of papers. There are empirical papers, which study empirically, for example, the correlation between renewable infeed and intraday market price features, or the behavior of volatility. There are a few papers on optimal strategies of a single agent in intraday markets. And there are also a few papers which did study the equilibrium price. But so there is also a recent paper, very recent paper just a few weeks ago, by René Aida, Andrea Cossa, and Nguyen Pham, who study equilibrium prices specifically in intraday electricity markets. And there are also a few papers on equilibrium in stock markets with optimal trade execution. In particular, papers by Sebastian Jaimungal, and I think one of these papers will be presented in the next session. All right, so now let me come to our model. In the model, we have n identical agents, and we denote by phi it the position of agent number I at time t, and we suppose that in the beginning the agent has 0 position, has not bought anything in the market. Then we assume, as is the case in classical framework like Algorithmic and Chris, that the position of the agent is an absolutely continuous process, and we define the rate of trading, which is the derivative of phi. Then we have a filter probability space which models the information available to all agents. And then we assume that the price in the market, everybody sees the same price, P and T, and this price is composed of the fundamental price, which is not affected by what the agents do, plus a market impact component. A market impact component is given by some constant times the average position of all the agents. So it's a sort of a permanent market impact component. When agents buy energy, this makes the price goes up, and the market impact is linear, because we want to be in a linear quadratic setting here. Then the agents trading in the market at time t, they also have an instantaneous cost, which has 2 components. So this is the usual, simply the cost of buying. If your rate of trading is phi dot, then the cost per unit of time you buy phi dot times the price. So this is the cost that you pay. And there is also the liquidity cost, which is quadratic, as in the Algorithmic and Chris framework, in the rate of trading. Okay, so the permanent market impact is modeled explicitly, but the transient market impact is modeled through this cost of trading term. This corresponds to a market where immediately available liquidity is low, so you need to pay high costs if you trade quickly, but the order book is resilient, so it can recover, and if you trade slowly, your costs are not so big. Now, each agent, so this is the specific feature of our market. Each agent has a demand forecast xt and aims to maximize her gain from trading in the market under the volume constraint. The strategy, the amount, the position, sorry, phi is the position at time capital T, must be equal to the production at time capital T, because xi little t for t less than capital T is the forecast of production, and at time capital T, the forecast becomes the realized production. So this is our volume constraint that is imposed at the end. And so if just the assumption, our assumptions are very, very simple, very general. We simply suppose that the fundamental price process is f adapted and square integrable, and the forecast processes are square integrable f martingales. So it is natural to assume that forecast processes are martingales, because if they are not martingales, if they had a drift, then you would be able to construct a better forecast by subtracting this drift. So forecast is the best estimate of the terminal value is naturally a martingale. And then we say that a strategy phi dot is admissible if it is adapted and square integrable. So only square integrability is the only basic assumption that we use in this paper. And then each agent would like to maximize the objective function, which depends on the strategy of this agent I, and also on the strategies of all other agents. Okay, and in the objective function there is the cost of trading plus the terminal penalty. So the terminal constraint is imposed through a penalty, not as explicit as exact equality, but we can also pass to the limit lambda goes to infinity and have an exact equality. All right, and this functional depends on the strategies of the other agents through the price, because in the price there is a market impact term which depends on the strategies of all agents, on the average position of the agents. All right, And so since the optimization functional of every agent depends on the strategies of all others, we are naturally in the framework of a non-cooperative game. And the solution is described in terms of as a Nash equilibrium. So we say that phi dot I, so this vector of strategies for all agents, is a Nash equilibrium for the n-player game if these strategies are admissible, meaning square integrable, and for each I, we have that the functional of ith agent cannot be improved if the strategies of all other agents remain the same. So basically, the strategy of the Nash equilibrium is when every agent has its best response, uses the strategy which is the best response given the strategies of all other agents. So I think it is a familiar notion for everyone. So standard Nash equilibrium. And now let me come to the main results of the work. We give basically the main result is an explicit form of the equilibrium price. We can also compute the strategies of all agents, but here for simplicity I only give the form of equilibrium price. And so this equilibrium price is given as the fundamental price plus a term which is explicit and which depends on the price, the fundamental price process, and the forecast process. So here we impose an additional assumption that the price is also a martingale. Then the fundamental price is also a martingale. Then the equilibrium price can simply be written as a stochastic integral with respect to the forecast and with respect to the fundamental price, where the coefficients are determined simply as integrals with respect to some coefficients of the model. N is the number of agents, and lambda is the coefficient in front of the liquidity cost. And if, in addition, we say that the terminal penalty is infinite, so we impose the terminal constraint as an exact equality, then the formula simplifies even more, and it no longer depends on the fundamental price. Well, this term is still there, but the other terms are simply integrals with respect to the forecast. Now, this is the simple case when S is a martingale. So what happens when S is not a martingale? In this case, basically, we need to replace the process S by another process which takes into account also the future values of S. So here we have INT, which is an integral over the past values of S, and I tilde NT is a conditional expectation, which also depends of some integral, which also depends on the future values of S. Right. So you see, if S is not a martingale, then it will have some drift in the future, and this drift needs to be taken into account. When we compute the equilibrium price. And the formula for the price is the same as before, except that the process S here is replaced by this process I tilde. All right. Now, to understand our results a little bit better, I will show you some asymptotic analysis which show how this fundamental price behaves in some limiting settings, and which allows to have some insights about the market structure. So for the asymptotic analysis, I make a couple of simplifying assumptions. First, the fundamental price is assumed to be a martingale. Now, the trading cost, I take it a constant. And also, I assume that the forecast process of agents have quadratic variation processes which are proportional to T. Some volatility sigma x and sigma check x. All right. Now, under these assumptions, the coefficients depend only on T minus S. We have this formula for the aggregate strategies of all the agents and similar formula for the price. Now let me move to the results. We have three categories of results, of asymptotic results. We have a characterization of the volatility, of the behavior of volatility, the behavior of correlation, and also the behavior of the gain of individual agents. So these are the three quantities that we study. With the volatility, however, there is a little problem. So since the strategy phi bar, the average strategy, is differentiable, in our model, with such a market impact model, the strategies will always be differentiable. The quadratic, because so phi is an absolutely continuous process. So phi bar, the aggregate strategy, is also always differentiable. And this means that the quadratic variation of the equilibrium price coincides with the quadratic variation of the fundamental price. So in principle, we cannot change the true actual volatility. However, what happens is that the drift of the fundamental price oscillates very quickly. No, the drift of the equilibrium price oscillates very quickly. And the actual observed volatility, which will be estimated on a discrete grid, may be larger than the volatility of the fundamental price. And so in order to have an idea of how large it will be, we use a proxy, which is given by the average of the square trading rate. So we use the square trading rate as the proxy for price variability, because the volatility cannot be defined. All right, and so if we look at this square trading rate, in the limit of small transaction costs, we have this formula. So it's given by the volatility of the fundamental price plus the volatility of the forecast, divided by the liquidity cost parameter, times n over n minus 1 and divided by a. So this shows that the extra variance, so this extra variability of the equilibrium price goes like A over alpha. A is the market impact, strength of the market impact, and alpha is the liquidity cost. So in other words, the decrease in liquidity costs will allow the agents to follow the forecast more closely, right? If the liquidity cost is lower, then you can be closer to the terminal condition. So you will follow, to be able to be close to the terminal condition, you follow the forecast more closely, and this leads to a higher volatility. Then also an interesting observation is that this function is increasing in n, the number of agents. And so the price volatility, variability of the price in this regime will decrease with the number of agents. In other words, the interpretation is that competition between agents increases market frictions and leads to reduced volatility. So when there are many agents, the agents on average trade less and the volatility is lower. And when there is only one agent, he will trade higher because there are more profit opportunities. He will trade faster and the volatility will be higher. Now, in the large liquidity cost regime, when alpha goes to infinity, in this case, this proxy for price variability decays proportional to alpha square. So in other words, when the liquidity costs are high, the agents will trade slower, and this will reduce the market volatility. And then in the large penalty limit, this proxy for price variability grows proportionally to lambda. So if the imbalance penalty is high, this is important perhaps for those who design market structure. If the imbalance penalty is high, then the agents will follow the forecast more closely, and this will increase overall the price volatility. This is the role of imbalance penalty. Now, regarding the covariance, we can write an explicit formula for the covariance between the forecast and the aggregate strategy, or the equilibrium price, in other words. And we see that this covariance increases when the terminal penalty increases, of course, and also when the time approaches the delivery date. So we recover this phenomenon that we have observed empirically, that the correlation between price and forecast increases when we get closer to the delivery date. And finally, regarding the gain of the agents, we can also compute the asymptotic of the gain functional when lambda, the liquidity cost parameter, goes to 0. It turns out that it converges to a finite constant. So in other words, when the cost per trade decreases, the agents will trade more actively so that the overall cost does not decrease as much. The cost for each trade will decrease, and then it will make you trade more actively, so that in the limit there is a non-zero trading cost still. Now, also interesting to look at the dependence on of this function on the number of agents. When n is large, the value of this functional is smaller than when n is small. In other words, when there is competition, when there are many agents in the market, then the cost of each individual agent will increase because of these additional difficulties related to competition of agents. And finally, in the large liquidity cost, the gain of each individual agent corresponds simply to the cost of do-nothing strategy. Right? If the liquidity costs are too high, the agents will simply stop trading. And also an interesting result is the behavior as function of terminal penalty. So when the terminal penalty grows, the cost of each agent will grow, but only proportional to logarithm of lambda. Because the agent can optimize her strategy, actually, even though the penalty is proportional to lambda, the actual cost paid by the agent will only be proportional to logarithm of lambda. So it will decrease much slower than if the agent did not trade. All right. And finally, to conclude, just a few empirical illustrations. Now, the goal of this empirical analysis is to show that not to calibrate the model, but to show that the model reproduces the stylized features of market prices qualitatively. Now, to do this, we use limit order book data from the Germany delivery zone that we had from Apex Spot. We compute the volatility and the correlation using this data, and then we compare these volatility and correlation graphs to what happens in our model. This is just an illustration of the market impact. So to the right, you have, so these are purely model-generated trajectories. To the right, you have a trajectory of the demand forecast as function of time to delivery. And then in gray, we have the price without market impact, the fundamental price. And in blue and red, so different notion of the equilibrium price. I will not go into the details of different notions because they correspond to the same curves here. But you see that the equilibrium price roughly follows the demand forecast trajectory, but it is much smoother than the demand forecast trajectory. There are much less oscillations. So the equilibrium price smooths out due to market frictions, liquidity costs in particular. The oscillations of the demand function are smoothed out in the equilibrium price. Now, the volatility. So here to the left, there is the estimated volatility, instantaneous volatility of the market. We use a non-parametric estimator with a bandwidth of about 5 minutes. And to the right, we simulated the price trajectory, and we used the exact same volatility estimator to estimate the volatility on the simulated data. And so we do recover, even though, as I said, the actual volatility, if the bandwidth goes to 0, then this will go to 0. But for 5-minute bandwidth, we do recover these volatility trajectories, which are different for different delivery hours, and which are increasing as we get closer to the closure of the market. So we do recover the Samuelson effect. Now, these are the graphs of correlation. And to the left, we have the correlation of empirical correlation between the price and the renewable wind energy production forecast in Germany that I also showed in the beginning of the talk. All right. And to the right, we have the price forecast correlation in our simulated model. Of course, it's very different because the model was not calibrated, but we do recover the same type of behavior with the correlation which is negative and increases in absolute value as we get closer to the delivery date. So the values are higher here than to the left because, so there are many reasons for that, but one of the reasons is that here we only take into account the wind energy production, but the actual prices are also depend on other renewable energy types like the solar energy. Okay. All right. So I think here I have getting close to the end of my talk, and let me just stop here to maybe have time to take a couple of questions. Thank you.
Thank you very much, Peter, and for this very interesting talk. So we now will open the floor. Don't close your slides, please, yet.
Okay.
Let me see from the audience if we have questions. If we don't have questions, I have a question for you. So, yeah, so while we wait for the audience to post questions, there is a question from Sebastian Jaimungal. He's referring to slide 28. If you could go to slide 28. He asks, is it correct that the epsilon Nash and the Nash are almost indistinguishable? How many agents was in this setting? Do you have some kind of epsilon Nash result?
Yes, we do. So actually, I did not speak about this in the talk because we also have a mean field component to the paper, but I did not have time to do that. But I do have a graph which illustrates convergence to the mean field. So on the left, we have a situation for 5 agents, and here we see that the actual Nash equilibrium for 5 agents is very different from the mean field equilibrium, but to the right, for 100 agents, we see that they are very, very close.
Yeah. He also comments, I realized that you have exact results for the n-player case, which is...
Yes, we do, because it's a linear quadratic problem, so we do have explicit results for the n-player case in the case of complete information. So we assume that everybody observes the forecast of everybody else.
Okay. Okay, I think unless there is any further question from the audience, I think we may stop here.